Welcome back to the Deep Dive. We're here to give you that knowledge shortcut, digging into the technical research so you don't have to.
Exactly.
Today, we're tackling something absolutely fundamental, microelectronics.
The real engine behind modern tech.
Seriously, think about it. Smartphones, advanced medical kit, aerospace systems.
It's all built on these components.
Components that are just constantly shrinking and getting wildly more complex.
And that's the challenge, isn't it? As things get smaller, the room for error basically disappears.
You can't just eyeball it anymore.
No way. You need really precise, non-invasive ways to see what's going on inside these materials.
Which brings us to today's focus.
Right. Our mission today is to give you a solid grasp of a really key technique here. Micro-X-ray fluorescence.
Or MicroXRF for short.
MicroXRF, yeah. If you're in semiconductor metrology or anywhere close, this is basically your cheat sheet.
We've gone through a stack of technical papers and industry analyses on this.
Yeah, looking at how it's actually used.
From R&D labs, right through to the factory floor, and even environmental checks.
It really covers a lot of ground. It's a versatile tool.
Okay, so let's start at the beginning then. Unpack this for us. MicroXRF. What exactly is it?
Okay, so at its heart, it's a way to figure out the elemental composition of something, what elements are present.
Right.
But the absolute key thing, especially for electronics, is that it's non-destructive.
Ah, okay. That sounds immediately useful. You don't break the thing you're testing.
Exactly. That's a huge deal when you're talking about expensive, complex components. You don't want to scrap them just to see if the materials are right.
Makes sense. So how does it work? How does it analyze without, wrecking the sample?
Well, it uses a very focused beam of X-rays.
Okay.
You shoot this beam at the spot on the sample you're interested in. The atoms in the sample absorb that X-ray energy.
And that does what? Makes them unstable.
For a moment, yeah. They get excited. Then, to get back to a stable state, they release that extra energy.
Ah, okay.
And they release it as other X-rays, secondary X-rays. That emission, that's the fluorescence.
So the energy that comes back out is the key, like a signal.
Precisely. It's like a fingerprint. Every element, gold, silicon, copper, lead, whatever, emits fluorescence at very specific characteristic energy levels.
Unique to that element.
Unique to that element. So the system measures the energy of these returning X-rays and how many it detects at each energy level.
And that tells you what's there and how much.
Exactly. What elements are present and their concentration right at that specific point you targeted.
Okay, and that micro part of the name. That must be pretty important given the scale we're talking about in electronics.
Oh, absolutely critical. It's all about the spatial resolution.
How precise are we talking? Because chip features are tiny now. Nanometers, right?
Right. Well, the kind of advanced micro-XRF systems we're seeing in the research can focus that X-ray beam down to a spot size as small as 5 micrometers in diameter.
5 micrometers. Wow. What is that like?
To give you some scale, that's roughly the width of one of your red blood cells.
Okay, that's seriously small.
And you need that level of detail. Think about analyzing tiny features on a circuit board or inside a chip package. Those bond pads, the traces, they're minuscule.
So you can pinpoint analysis right onto those features.
Yes, and crucially, it lets you do elemental mapping.
Mapping. So you scan across the surface.
Exactly. You scan the beam across an area, and you build up a picture showing where each element is located. Is the gold coating only where it should be? Has some contaminants spread? The map shows you.
That 5-micron resolution? I can see how that's the difference between success and failure.
It really can be. A reliable product versus a huge recall.
Which leads us straight into its most immediate use case. Reliability. Day-to-day manufacturing. Let's talk quality control first.
Yeah, this is a big one. MicroXRF is right there on the front lines, helping prevent failures before they even get a chance to happen.
How so? What are QC teams doing with it?
Well, standard procedure stuff, but crucial. Checking incoming raw materials. Does this batch of material meet the specs?
Verifying suppliers.
Right. And then perform on routine checks during the production process itself. Spot checks to make sure everything stays consistent.
And it's good at finding things that shouldn't be there. Impurities.
Definitely. Our sources really highlighted that. Detecting substandard materials is key, like inconsistencies in solder.
Solder used on circuit boards.
Exactly. If the solder mix isn't quite right, maybe too much tin or traces of some unwanted metal, that joint might seem okay initially.
But fail later.
But fail down the road, maybe years later. Catching that tiny variation in elemental composition early, that saves enormous costs and headaches later. Warranty claims, reputation.
Okay, so that's proactive TC. But what about when things do go wrong? failure analysis. This seems like where the non-destructive part really pays off.
Oh, absolutely. It's a lifesaver here. When a component fails, you need to know why. But often, the traditional ways to find out,
Involve cutting it open, grinding it down.
right, destroying the very evidence you need to examine.
Yeah.
MicroXRF lets engineers look at that failed component, zoom in on the failure site with that 5-micron precision, and see the elemental composition without disturbing it.
So you can find the material defect or the contamination right where it caused the problem.
Exactly. You can pinpoint those elemental inconsistencies that led to the breakdown.
And those elemental maps you mentioned must be invaluable here.
Totally. The sources had some great examples mapping complex packages. You mentioned BGAs, QFPs. Maybe we should quickly clarify those.
Good idea. For listeners maybe not deep in packaging, what are BGA and QFP?
Sure, they're just common ways integrated circuits, the chips, are packaged to connect to the circuit board. BGA is ball grid array.
Little balls of solder underneath?
Yeah, whole grid of them. Surface mount. QFP is quad flat package. That's the one with leads, like little legs coming out from all 4 sides.
Got it. So pretty complex structures.
Very dense. Lots of connections in a small space. When one fails, mapping the elements on the surface, the copper traces, gold plating, nickel barriers, the solder itself, it can immediately show the analyst where something went wrong. A crack, corrosion, a material breach.
So like the example on the source, if a wire bond inside failed because maybe laser etching nearby was too aggressive, the map would literally show an anomaly in the gold or copper signal right where that bond broke.
Precisely. You'd see the distribution is wrong. It gives you clear, visual, actionable data. You can see why it failed and feed that back to manufacturing to fix the process, prevent it happening again.
Okay, so it's fantastic for troubleshooting for reactive quality work. But let's shift gears a bit. From fixing today's issues to creating tomorrow's tech, how does MicroXRF help in R&D?
It's really fundamental there, too. Think about material characterization.
Developing new material.
Exactly. So much innovation in electronics relies on finding materials with better conductivity or better thermal properties or more durability.
Right.
If you're synthesizing a new alloy for interconnects or tweaking a dielectric material, you need to know its exact elemental makeup to understand and optimize its properties. MicroXRF gives you that precise data.
That atomic level insight needed for development.
Yes. And then there are coatings.
Ah, yes. Coatings are everywhere in electronics for protection, performance.
Absolutely critical. And often these coatings are incredibly thin, just a few microns thick.
Hard to measure accurately.
Very hard with traditional methods. But MicroXRF excels at coating analysis. You can measure the thickness of these ultra-thin layers precisely.
Which is vital, right? Too thin, it doesn't protect. Too thick, it's wasted material or might cause other issues.
Exactly. And it's not just thickness. You can check the uniformity of the coating across the whole part. Is it even? And you can verify its composition. Is that gold layer pure? Is the nickel barrier intact?
Down to that 5-micron spot size again. So
Yeah.
an engineer can be sure that protective layer is exactly right everywhere it needs to be.
Precisely. And that loops right back into process development. Well, R&D teams can analyze components at various stages of a new manufacturing process without destroying the samples at each step.
Ah, I see. Continuous feedback.
Right. They can track how the materials are changing, identify any subtle deviations or inefficiencies in the process flow as it's being developed. It allows for much faster optimization and ensures the final process delivers high quality consistently. It's non-invasive process verification.
Quality, failure analysis, R&D. It really touches many bases. But there's another big piece, the bigger picture stuff. Environmental compliance.
Yes, that's a huge area. And increasingly important, MicroXRF plays a vital role here in environmental monitoring and regulatory checks.
This brings up global standards, market access.
Yeah.
It's a major factor for manufacturers now.
Absolutely. The industry is under immense pressure worldwide to make products that are safe, sustainable, and compliant.
And MicroXRF helps ensure that.
It's indispensable for it, mainly because it allows for rapid screening. You need to check a lot of components quickly.
And the big regulation here is RoHS, right? Restriction of hazardous substances.
That's the main one everyone knows. It dictates what materials can't be in electronics sold in major markets like the EU and many other places.
Banning things like lead, cadmium.
Exactly. Lead, mercury, cadmium, hexavalent chromium. Specific hazardous substances are banned or strictly limited. If your product contains too much, you simply can't sell it there.
So how does MicroXRF fit in?
It's used specifically to detect these banned elements, quickly and non-destructively.
Ah, so instead of sending samples off to a lab for slow, destructive chemical testing,
Which takes days and costs a lot.
a manufacturer can use MicroXRF to screen components, maybe even finished products right there, on the line or near it.
That's the idea. High-throughput screening, it dramatically reduces the risk of non-compliance and the huge potential costs, fines, recalls, market bans.
So it supports designing greener electronics from the start.
Yes, it helps ensure the product is compliant before it gets shipped. It's a tool for risk mitigation, really, and sustainability assurance.
Wow. One technique really does span quality, innovation, and compliance. It's quite remarkable.
So if we were to sum up the value here, MicroXRF is it's this incredibly versatile but also highly tailored solution.
Tailored how?
Well, you can configure the systems for specific applications, QC, R&D, RoHS screening, but the core benefit is always precise, reliable elemental data.
Right across the board.
Right across quality assurance, research and development, and that critical environmental monitoring piece. It brings clarity, certainty to this world of ever-shrinking, ever more complex devices.
Okay, so for you listening, let's nail down the key takeaways from this deep dive on MicroXRF. 3 main points.
Go for it.
Number 1, remember it's non-destructive and high resolution. That's its superpower. Elemental analysis without damage, down to that tiny 5-micron level.
Essential for valuable components. Takeaway 2, it's crucial for quality and reliability.
Right. Checking things like solder consistency, analyzing coatings, and performing detailed failure analysis using those elemental maps on complex packages like BGAs or QFPs.
Finding the root cause without destroying the evidence.
And number 3, it's a key enabler for sustainability and compliance, helping companies meet regulations like the RoHS directive by quickly screening for hazardous stuff like lead or cadmium.
Yep. Fast, non-destructive compliance checking.
It really seems indispensable now.
Well, think about it. As microelectronics keep shrinking, heading towards, sub-micron features, the ability to see the elemental makeup at 5 microns without destroying anything, that fundamentally changes the economics of quality control. And R&D too, faster prototyping.
Absolutely. So here's a final thought to leave you with. Next time you pick up your smartphone or rely on some advanced tech, remember the layers upon layers of complexity inside. Every material, every tiny trace, every coating had to be just right, verified. What hidden material flaw, what surprising inconsistency might MicroXRF be uncovering right now in the next generation of these devices?
It makes you think about the invisible checks that underpin the reliability we just expect, doesn't it?
It really does. That hidden complexity behind effortless function. Okay, that's all we have time for on this deep dive. Thanks for joining us.
Yeah. Thanks, everyone.
We'll catch you next time with more insights from the cutting edge.